everyone. Welcome to Rubber Industry Tech Talk. It's a techno-based activity. Today, we're all here for this topic on the improving prediction of rubber compound formulation, GrafCompounder case studies. This presentation is given by Dr. Hans-Joachim Graf. As you know, this program is managed by Technobase. We do have partners to support this program. I'd like to thank our partners, Rubber World. And Rubber World is a 135 or 130 plus years old magazine, especially in rubber technology. It's a free to subscribe. You can subscribe at rubberworld.com. And also we have other magazine, Rubber and Tire Digest, which is joint publication of Technobase and Rubber World. You can also subscribe it free in a digital format, rubbertiredigest.com. And also important Technobase channel, Rubber Industry Network, and also Rubber Technologist Global Network. I welcome you all and thank you for supporting this program today. So now we are here for the program on today's talk, Rubber Industry Tech Talk. The topic is on the improving prediction of the rubber compound formulation, GrafCompounder case studies. This presented by Dr. Hans-Joachim Graf. And Dr. Hans-Joachim Graf, he has more than 45 years experience and in the compounding, material development, processing, and he also trains the people with the industry people, so for a training program. And he developed this GrafCompounder program, which is a very useful tool for the people who develop formulations. And today, Dr. Graf will be talking about how to improve the prediction of the rubber compound formulation. Dr. Graf, over to you. Let me ask you to share your screen.
So welcome from my side to this seminar, which is the second one in a row of GrafCompounder introduction and explanation how to use that. And now we want to discuss how we improve the prediction of rubber compound formulations. And this should be supported, or want we to support, with some case studies. So the content of this webinar would be why we need proving the prediction, why we do that in this form and why we need that, and a little bit about analysis of data. We know that we do that statistically with in a DOE schematic, design of experiments system, and here we want to expand that a little bit with so-called correlation analysis, which we can do in both systems in the design of experiment software, at least in some, and with the GrafCompounder as well. And then I would show how that works in some case studies, which I have at the moment finished so far, and we will end with a conclusion. What we have on data is a question and how we use that. That was the origin of the invention of the GrafCompounder software, because with the massive data everywhere in the industry, in personal reach, or in literature, we have a huge knowledge base, but we have a limited use if we try systematically to investigate that or try to extract the knowledge from that. So what we do in practice is that we do experimentation again, and this way we spend a lot of money. So, and in the GrafCompounder, we have already a tutorial files, which are samples out of the literature, for example, or mostly out of the literature. And that deals with NR, with EPDM, and with other polymers. And this is a very short data set, we said you can already practice. So when we talk about correlations, then we look back to the science of rubber and how properties have to fit together. Here you see a correlation that is hardness and modulus 300, left side. And you see there's somehow fair correlations. At least you acknowledge that there is some correlation. It's not good, so a correlation coefficient will probably be low. And then when you do another graph where you have a correlation, a scatter plot of tensile over elongation, then you see by sudden there is no correlation. And then we have asked ourselves, would there a correlation? Or is it really to accept that there is nothing? What is actually a correlation? To be clear on what we are trying to do. So it's first of all a statistical measure, and that describes that two variables are related to each other. Is not meaning that there is a relation which you can describe analytically. Yes, we are in pure statistic, so we can create a graph, we can create a regression line, and we can create a correlation coefficient. And this is only statistic meaning. So we have no cause and effect yet identified which describes this type of relationship. That is very important, yes, because we need to do that actually in step 2. So now with this slide, I want to remind you on famous graph that was published by Daniel Hertz in Elastomerics 84, and he took that from a booklet, Technology, Science in Technology and Rubber, and Koran has published that in the chapter about vulcanization in 94, and that describes the dependency of properties from crosslink density. And just let me say crosslink density is some sort of a master term in rubber industry. And what you see here is that some properties are linear dependent from crosslink density, yes, and some properties are non-linear dependent from crosslink density. For example, the tear strength, fatigue life, toughness, and things like that. At least when you see this type of graph, you should see as well that if there are linear dependency, for example, hardness and static modulus in an experimentation series, they should show some correlation. Here's some linear correlation as set to hardness and modulus. I can add this dynamic modulus. And the nonlinears are, for example, tensile tear, hysteresis, permanent set, friction, and probably properties after aging. So the point is for this presentation here that if that's true, we can have beyond the statistics of experimental design a tool to improve our data. In other chart here where the correlation between loading and physical properties is described. So you have here tensile versus carbon black loading. You see that tensile depends in a nonlinear way from the carbon black loading, and it's also different for different carbon blacks with different surface activity. But if you go at a definite loading up here, yes, you would then suggest there's at least some room for linear correlation. And when we investigate now a little bit deeper correlations here, so we see that there is a linear correlation with hardness and static modulus, and there is a nonlinear correlation as in the previous slide from tensile and tear. That's very basic things we need to remind ourselves to understand what I want to say in the following. When we see the stress strain curve, yes, here's a very schematic drawing of the stress strain. So that's this tension over elongation. Then normally we take the modulus at low elongation a little bit as a sign for cross-link density, which moves up slowly with the activity of the filler. Yes, and the difference between this modulus, or even better, the Young's modulus, with an elongation as a 300% elongation, yes, in the past we took as a measure for cross-link density. So what is pointed out here is that there should be a correlation at least between modulus at lower elongation and the modulus at higher elongation. And that is in conjunction with the energy at break, for example. And so at least we should see here, when we have data which are accidentally composed of a data set, is that the modulus should be somehow correlated to each other. So why is that so important? When we go in statistic experimental design, yes, and we have the statistics to decide whether we have a significant influence of a factor on a response. So, for example, of a carbon black on the modulus, then we argue with the distribution of data and how good that will fit by a regression line or a regression curve is a second order. In a diagram here, as shown here, as for example, the modulus 100 over modulus 300, yes, we judge with our view on the accuracy of, or the good fit on a regression line, which we can place here with our imagination, yes, and then when we do that, we see immediately, oh, there are here some points sticking out. And the question is it possible to take these points out and this way improve the correlation, and then finally can use this clean database and for better prediction. Sorry. So if you see now hardness over modulus, as we know as technologists, that this modulus represents a portion which comes from the cross-link density, as a little bit explained very briefly with the stress strain curve, and the other portion comes from the cross-link density, then there should be, at least as some sort of integral property, existing a hardness over modulus 300 as well. So when you compare both curves, you see there is a larger scatter of in the graph of the hardness over modulus 300. And then the question is, why is that? Is that this way? Is that natural, or is that actually due to our experimentation and lack of precision? So here I have now put in the graph the regression line on the left side. Yes, and indicated 2 points, which I would then say they could be possibly outliers, or they are not fitting in this correlation. And from this, I can now investigate these 2 compounds or take them just out. So both possibilities are there. If I do that, of course, yes, then you see that my regression line would shift. Yeah, that so all if I work that way, yes, and I eliminate something, I need to do my regression analysis again without this point which I eliminated, and then I would come in terms of statistic experimental design to an adjusted conclusion. And in this case, when we clean data, yes, with a certain distance from this regression line, I can do that in my program by a mouse click. And then I see those compounds name. And with that, then I can go in the database and then right click on the name and then eliminate that, and then I refresh the graph. So that is 2 mouse clicks away in experimental design. Yes, I need actually to eliminate only this date from that compound. This is an exercise you can do. On the other hand, your compound in total is suspicious, because normally one measurement error could be accompanied by other measurement errors, or the compound in itself has some problem due to variation coming from some sources. So then we should remind ourselves what is accuracy and what is precision. Yes, and in this scheme, I have taken from a very nice publication in Elastomerics from '83. I see that on the right side, yes, I have poor accuracy and poor precision. You see a larger scatter around the target. And when I go to the left side, yes, I improve my accuracy, and still my precision is poor, yes, because I have a larger scatter around my target. And you see, when all my data are, let me say, in certain range, I have a good precision, but I missed the target. So my accuracy is poor. And then if I'm inside the target with a short distance and all my points are somehow near to each other, then I have good accuracy. The problem here is that we are in practice, we are not paying enough attention to that. That means if I'm backwards analyzing a lot of DOEs, statistic experimental design, which I have in my life. And I use this simple correlation technique. I was a bit shocked about the precision and accuracy we are not seeing in the statistics of this way, only in the correlation graphs and in the predicted versus actual curve. So I need to show in certain graphs, and the statistic values are not a good guidance for precision and accuracy. So where all this influences disturbing our accuracy and precision, what we need to think about, for example, when we do our experimentation, mostly in a laboratory mixing machine, yes, we have some sort of, let me say, standard practice. First of all, most of laboratory machines are much less equipped than mixing machine in a production. So you can have access, you have less access to good data out of this machine. Mostly the machine is very old because it's not productive, yes, from the standpoint of an investment. And then you have raw materials, which you get from somewhere. You have a lot of raw materials to manage, and they can be pretty old. Yes, and when you need a fast test and answer for something, yes, and you then searching for raw material, and you would then take what you have in your warehouse, in your laboratory shelf, and that is maybe out of date or whatever. Yes, I see that in practice. That is a type of problem which, because we are forced to keep the costs in the laboratory down, so that will give us some influences on precision and accuracy. So then we have our standard test protocols. And here's the question: when we do 3 samples, I think that is mostly used in the world that way. Yes, is that enough? Do we not should do more? In other terms, when you do statistic experimental design, yes, and then the software asks you anyhow, you should have some repeats, and mostly people, let me say, scale that a little bit down. Instead of 5 repeats, yes, they do 2 or 3, and I did that as well. It's actually mostly 1. Then you have your gauge R&R study hopefully done. Yes, that you know exactly what type of measurement error you have in each test. I'm not sure if that's done everywhere. So I talked about already the repeats, and to improve accuracy and precision. Yes, we offer since a long time so to organize round robin testing. That is an institute in Germany, for Germany, which is doing that. And here you should train your laboratory staff in precision and accuracy, that they finally know exactly where they are and what needs to improve. I make a conclusion here, yes, because I found some friends in industry and asked them, what do you do for precision? What is the problem when I'm saying that we need to improve precision? Yes. And the answer was from all of them, yeah, we know that problem. Yes. And it is complicated. So we are cautious with interpretation of data. And we try to do some more than comparing A and B compound, because the question what is the measurement error when you compare that is a significantly different, is mostly cannot be answered this way. So let's do an example here from literature, which is published. At least it is made in '98 from my friend Rajan Vara with some colleagues. And that was a very challenging screening test because of the lot of factors chosen. And that is the ENB content, the sulfur, and the some accelerators. And with this here, I investigated for the first time, or investigated this repeatedly, excuse me for that. And I saw the problem, first of all, to manage experiments with 48 recipes to do in a lab in a short time frame, and then stay ahead with all the arguments we had already exchanged. So when you do the type of scatter plot, in this case, for example, you plot tensile over elongation at break, you see immediately that you have some sort of correlation, yes, but you see also there are a lot of data which are not fitting very well the imagined regression line. And you see here my R square, my coefficient, my correlation coefficient is a little bit less than 0.6. So I thought, wow, that is an laboratory known for high precision and value. Everybody knows that, yes. So it is a little bit hard to accept that they only got a correlation coefficient of 0.6. And when you see now the scatter plot of this, yes, you know exactly what means 0.6. So when you see now when I take some of the data out here, yes, eliminate them in this plot, yes, and then we go to the right graph, yes, so then you see my R square, my correlation coefficient goes now to something larger than 0.8. So, and if you're taking my previous explanation on words for granted, then you have to ask, is 0.8 enough for a good precision if you use a software like the compounder software? And I will at the end explain somehow why I'm stressing this point. So when we saw our correlation graph crosslink property over crosslink density, yes, then we have a very good measure for crosslink density, and that is the force in a Volcammeter experiment. Yes, that is the F max minus the F min. Here it's another abbreviation that is MH minus ML, so that's a F max is MH and F min is ML. So when the modulus 50 is measured in this study, there's a lot of data taken, and then you see again, yes, that we have some sort of points sticking far out. Yes, and if I clean that a little bit, yes, you see that my correlation, which I now put a lower and upper limit in terms of lines here on the right side, were a little bit narrower. Yes, and it's almost a good correlation. Yes, and I have to deal with these experiments here to either redo them, repeat them, or actually investigate why they are sticking out, to learn something about my experimentation and the experiment itself. So if we go now and load the program to show how that works in the GrafCompounder, then you see here the screen of the GrafCompounder and 2 words to the software. Yes, you have your input data where you have your ingredients column on your property column, and you have then now your recipes one by one. And you see that is I put all the recipes in here, and I take that because from my side it's sometimes easier and faster to analyze your database. In this case, can be small or big. And precision, as we have already talked about, is if I name this software as a so-called feed-forward artificial intelligence software, because the mass of such a system is behind that, yes, then you have no ability at the moment to adjust the outcome, which would be here the output. When you do a query and you get the mixture formula here, because we have no machine learning element included. And that is a big problem in its own. Yes, the machine learning requires big data and very fast learning cycles. So if you see face recognition or something like that, or spell checking, yes, that goes, you can make these adjustment factors and incorporate them from fast forward to recurrent in a way that you have no really, you just have to have patience to put those data in. But in the rubber industry, yes, we have a time between the experiment and the getting results, which are days or weeks or even longer than months. Yes, if you think about stress strain relaxation experiments or whatever you think about that, yes, they're taking a lot of time. So to do those training is a tremendous effort. And we don't have that at the moment. Even thought about that, how to manage that. So in this case, I try to gain data in a systematic way, that is this one, and then, let me say, analyze or make a prediction with such a database. Then improving my data. So when I do that this way, I first of all can just do a 2D scatter plot as we have seen. And that means I choose, for example, my MH minus ML, as we have seen, and then I go and check where is that here, hardness. Yes, and then you see that you have a scatter plot like this. And then you can now click on, yes, each point, and this way you can identify the compound, and then you can go in the compound. And this way, I can now go in my database, and that is compound 48, for example, and go here and eliminate 48. That's the last one by right click and go back in my screen here. Yes, and then I say refresh recipes, and then the point is gone. Yeah, so that's one way to do that as described. So I make that small and go back to presentation. So you see here I have done that, and in this way, when you now go in a question, what from the outcome of this experiment, what would be the best? Yes, and you put in a criteria window your specification, and then you make a confirmation experiment. And I assure you that this confirmation experiment is in the 95% confidence interval, as well as a prediction tool in the DOE software. Yes, and I had to learn something that, of course, when you do a regression analysis and describe your point by a regression equation and then do your prediction with that regression equation, you have nothing else done. Then you have smoothed your data, adjusted all your data to this regression equation here. And by this, you have taken, by this technique, automatically this, let's say, them outliers out. So when we have another example, yes, here is the question. Those experiment I have described before is obviously done in a laboratory mixer in a laboratory. So they have made 48 batches with that variation. Yes, and then is the other question is, if we use a master batch, would that improve our situation? Because when I'm doing an accelerator investigation, I would then have a master batch and incorporate my accelerator systems on the mill, which is another treatment than in the mixer. And the question is then, is that giving us some relief? So I have here a so-called accelerator screening for mostly the target was to look at the best accelerator system for dynamic usage, which is around 220 examples. Yes, with different sulfur accelerator combination and sulfur first accelerator, secondary accelerator combination, which you can extract from that data. So, and when you put that in a DOE program, you have first of all a hard time to see anything. But when you do, for example, residuals versus run, yes, you might see a type of pattern here, yes, which can become from somewhere, at least also from the operator attitude, for example, to make a break at certain times, yes. So that is an impression of this data. And you see, of course, the spread here in the statistic, external studentized residuals according to run order. So what we have done here is the sulfur level, 2 levels, 0.6 to 2.5. And then you have all the accelerator known at this time in molar proportion. Yes, not in PHR proportion, in molar proportion. So if you do a diagnostics, yes, you see here actual over predicted for the so-called dynamic hardening, yes, you see a certain correlation, yes, but that could be nonlinear, yes. Why? The nonlinear regression will you not show any improvement over the linear regression. That was also a little bit, so this data here are outside this line, are not so important for the regression analysis. That's a little bit surprising, but that is statistics now. If we go to the next slide, yes, and put that all in the GrafCompounder program, you see, first of all, on the left side, the scatter plot from the program I have shown. And that is very similar to the tool inside the DOE program, where you can those analysis today in the version, in the newer version as well. Yes, and you see this, if you ignore the scale for a bit, yes, that this is almost the same. So with the GrafCompounder, yes, and clicking on all these compounds here by name, and then going back and forth in the data sets, yes, then you can easily identify all the compounds. And in the next slide, when I'm doing that for a portion of this data, yes, where I have sulfur at 2 levels and only the sulfenamide TBBS here at 1.5 PHR, then you see some sort of correlation here, and you are disturbed by this here. Yes, because that seems not to fit. Now with the ability to click, yes, I can tell you, okay, this here is all at 2.5 PHR sulfur, and this here, all these points are at 0.6 PHR sulfur. Yeah, so the hardening factor here is very, very different than from that, and the correlation seems to be different. So now you can analyze that. Yes, so we have this cluster there, and we have another cluster along this line. Yes, so that would be a conclusion now that I can say, okay, for low hardening, I think I made a mistake, just is higher sulfur, and then other properties are not that important. And for higher hardening factor we see with 0.6 pHr of sulfur. Have that screen on your computer now, all the data, and I just scroll sideways that you see how this experiment is done. It is a traditional screening test, at least a large screening test, a lot of effort. And let's go to a diagram, do the scatter plot, and select some of the most interesting data here. That's, for example, let's take tangent delta, and let's take the dynamic hardening with abbreviation VRF. So when you see that, okay, yes, there's a brilliant, yes, there must be a correlation. When you look a little bit closer in this picture, yes, you see here staples of points, yeah, which you can now, of course, go through, and then you will identify that this staple of points have a certain correlation with the compound and mostly with the sulfur level. Yes, and the accelerator used that way. So that has you have here probably a sulfur level, yes, and then you see that your hardening factor is increasing that way. So you can analyze now every accelerator behind these compounds, which are given here in this small window. And then you can group those accelerator by chemistry, and then you have a certain impression about the action between accelerators in this environment with a first and secondary and the hardening factor. So that was a way actually to find out what is the best for this. If I go that, take that out again, and make that small, and go up aktuelle Folie. So that's, you understand now this way what is behind such a plot, which is in this case only the portion with TBBS and only one accelerator involved. Of course, you see that we have some sort of problem with the scatter and with the measurement errors with that trial. Actually, I can say the work was very, very good in terms of what we have in mind as precision. Yes, for a forecast, in general, for a prediction is somehow useful to have a very first idea. Mostly it needs a DOE with that predicted to learn some more about this predicted compound, and then judge on your prediction. So if we go to another example, that is an RIR compound. Here I lumped together some sort of DOEs, design of experiment portions made at different time in the same laboratory, and that is dealing with some sort of a sulfur accelerator combination with some sort of in mind. At this time we had, for example, worked on reversion. So the very old data from my past position in a company which are dealing with ingredients in rubber. So when you do that, yes, then you have a tool in GrafCompounder which is ingredient frequency distribution. And in this case, you see that we have some accelerator somehow distributed and some are not. So that is a view on your database. And when you go to the fillers, for example, here you see we have only 2 levels of fillers, and here something in between. And here I have only one main portion for oil and a couple of compounds with a smaller portion of oil. So we have a type of uneven distributed database. It's not really anywhere near a so-called nice distribution of data, so that from then artificial intelligence point of software, yes, you have always to jump over large gaps when you now do your query and then walk your mathematically to search for the solution. So how that looks like, yes, in our correlation plots. For example, here we have Volcameter Fmax minus Fmin over modulus 100. Actually, I personally would expect there should be a better correlation. Yes, but it isn't. So then the question is, why is that? Yes, okay, we know that in Fmax minus Fmin Volcameter value, we have 2 things which we see, that is the crossing density plus the reinforcement from the fillers. And we saw that it's somehow different. And in the lower modulus, we, let me say, see a little bit more of the cross-link density. What I want to stress here is the difficulty in a Volcameter measurement of the Fmax, because if that is a matching modulus, then your Fmax is actually determined when you shut off your experiment of your measurement experiment. Yes, because it's if you would measure longer, yes, your Fmax will be at a higher value. So if you have not really a maximum in the Volcameter curve indicated by the first derivative and 0, then you have no real, you have a measurement problem here. Yet with this classical, we had that all the time. And that was discussed extensively inside the companies very often. Yes, and we accept certain measurement procedure, but it is really complicated to deal with such an factor if this is not controlled. Yes, on the other hand, we have a good correlation if we correlate modulus 100 to modulus 300, for example, and then we have some sticking out here, yes, which we can then analyze and think about. So if I do that, for example, with tensile over elongation, I see that I'm not sure if I should proceed with just a database, because you see a lot of data are really sticking out. So yes, I analyzed some of them, and they were all a little bit exotic, but after so long time, I'm not able to identify the root cause of this and what went wrong with this type of compound. Yeah, and when you clean a little bit the database, you see that your correlation becomes a little bit better. Yes, but not really good. You see these points here moving here to this side. Yes, and it seems a little bit that the correlation in this type of data set is not linear. So when we do a further example and take a normal trial and error study, I think that is more of interest than those type of data. And in this case, we have some sort of polymer variation. That's all EPDM. We have a very different sulfur accelerator combination and different loadings. Not too much difference, but some. So here in the first slide, from this type of trial and error, you see there is somehow a correlation between hardness and modulus, which I easily can deal with. Yes, because when I put some of this data out, then I can improve my correlation quite well. And then I already see, yes, there is a correlation improvement this way, yes, with the elimination. The remark I have to make is, of course, you need to analyze if it's justified to keep that out. So when you see here a tensile over elongation now, there's a quite nice correlation. Yes, if you eliminate some points, which I would say obviously measurement errors, yes, and when you go in the module 100 over module 300, yes, exactly these points here are missing here in this. That is very interesting. So that gives me a good reason to go in the analysis of the experiments and or better probably repeat the experiment to verify that this is all justified. And we go again in the program, because this is one of the most interesting experiments of my last. So what was the reason of this trial and error procedure? It was a search for a compound with a high heat resistance to higher heat. Yes, and it is mostly measured with the compression set. Yes, you see we have some compression set at 150 C. That was one of the target which we tried to achieve with this compound. And when you have made your data, okay, you sometimes have the feeling, oh, I get it soon, or I missed it this time, and then I need to do this and this and this. Yes, a typical trial and error procedure. You fool a little bit around, and then you hope that you get some sort of a solution. So after you have done this, yes, then you are able to analyze this with software like the GrafCompounder, because you cannot hardly put that in a DOE software for analysis. And we can do those scatter plots, of course, to analyze that data. But here, in this case, we have the criteria window, and I just put all my target, my specification, in this criteria window. And when I do that, yes, then I have an result. And you see that here I neutralize that a bit to protect the owner of this. And that is that we need a little bit of polymer 2 to actually increase the stability against heat. Yes, and then you see also that we have compression set at 150. See the range in this experiment is from a little bit less than 10 to 30. I think normal is something around 20, which is quite good. Yes, but here the challenge was a little bit, the bar was a little bit higher. And then all the other aging movements here, you see delta tensile and so on, should be around 0. Yes, and then when you then make your prediction, you come very close to that type of targets. And that is also verified in practice. So that is, for me, a good sign how good is prediction when you do just have trial and error data. And this, as I said, I want to improve with that type of correlation analysis, yeah, which I have shown here, to inactivate the compound in the data set, take them out just, and then work further down the road with, let's say, a data set without obviously data with a larger measurement error. So I hope I have shown you that how to use that, and I hope I have shown that we need to pay more attention when we do development to have a better view on such data. If you go back in this presentation, you see that we have properties which are somehow robust and not so dependent on measurement errors. For example, the modulus, the hardness, I'm not sure anymore, because that is somehow disturbing what you have when you analyze that way. And if you go to sophisticated properties like tangent delta, like C static, static force or dynamic forces and things like that. Yes, or into aging, of course, then you become more and more sensitive to precision. And you see obviously the point that we need to have to increase our precision when we really want to analyze that with any software, either GrafCompounder software or statistic experimental design. So with that, I'd like to thank you for joining this presentation, and I foresee a couple of questions, and I'm happy to answer them all. We have taken or offer our time here for you, and with that, I thank you again, and any question, let me know further, and more information you can get under my website, GrafCompounder.com. So thank you very much for your attention.
Thank you, Dr. Graf. As Dr. Graf has mentioned to all of you, you can visit for more information on the GrafCompounder, GrafCompounder.com. You'll find how to order or all the frequent asked questions and also tutorials, how to utilize this software. So I'm sure that you definitely benefit from this GrafCompounder program and make your life easier. If you're a compound development person, I think this is one tool that you should have it in your office or factory. Okay, so please visit the website grafcompounder.com. And if you like to view this presentation, what happened today, you can go to our Technobiz channel and you can view this program in a presentation today. Okay, for that, with that note, I thank you all. Thank you once again, Dr. Graf, for joining this Rubber Industry Tech Talk. And I'm hoping to see all of you in the next session of this subject. Thank you all. Bye-bye for now.